Nonlinear system identification is an important topic in system modeling and control engineering. While many engineering systems can be approximated using linear models, real-world processes often exhibit nonlinear behavior that cannot be accurately represented by simple linear equations. The objective of nonlinear system identification is to learn a mathematical model directly from measured input-output data, while capturing these nonlinear dynamics. In this video, we will introduce the basic idea behind the nonlinear ARX models and see how nonlinear regressors and nonlinear mappings can improve modeling accuracy. Let's begin by considering this two-tank process. Although it may look relatively simple, the relationship between the input flow and the output level is nonlinear because of the underlying physical dynamics. If we try to describe this process using a purely linear model, it may capture the overall trend, but it will often miss important nonlinear behaviors. Our objective remains the same. We observe the measured input and output signals, and we want to identify a mathematical model that can accurately predict the system output. The challenge is finding a model that is flexible enough to represent these nonlinear dynamics without becoming unnecessarily complicated. Three ways to increase model flexibility. Let's start from the linear ARX model. The linear ARX model uses past inputs and past outputs as regressors and combines them using a linear equation. This approach is simple, computationally efficient, and easy to interpret. However, as the system becomes more nonlinear, a linear relationship may no longer be sufficient. The first improvement is to introduce nonlinear regressors. Instead of using only past inputs and outputs, we can also include nonlinear transformations, such as the square root or the square of previous signals. These additional features help the model capture hidden nonlinear dynamics. The second improvement is to replace the linear output mapping with a nonlinear mapping. Instead of computing the output using only a weighted sum, we allow a nonlinear function such as a neural network or a sigmoid network to learn much more complex relationships. By increasing the flexibility of the model, we can often achieve significantly better prediction accuracy while still using the same input-output data. Now, let's see how all of these components work together. Just like the linear ARX model, we first construct a regressor vector using previous inputs and previous outputs. But now we can also include custom nonlinear regressors. These nonlinear features are combined with the original regressors and passed to the output function. The output function consists of three parts. First, an offset term, which captures the consistent bias of the system. Second, a linear mapping, which models the linear behavior exactly as in the classical ARX model. And finally, a nonlinear mapping, which captures the nonlinear dynamics that cannot be represented by a simple linear equation. The contributions of these three components are then combined to generate the final predicted output. So, the main idea behind the NLARX model is straightforward. We keep the familiar ARX structure, but extended it with nonlinear regressors and nonlinear mappings to better represent complex system behavior. To summarize, nonlinear system identification extends the traditional ARX framework to model more complex system dynamics. There are two main ways to improve the model. First, by introducing nonlinear regressors. Second, by replacing the linear output function with a nonlinear mapping. These additions allow the model to capture behaviors that are difficult or even impossible to represent using a purely linear model. Overall, the NLARX model preserves the intuitive regressor-based structure of the classical ARX model while providing the flexibility needed to accurately model nonlinear systems. And that's all for this video. Thanks for watching.